We've been talking a lot about the different trig functions and their graphs and so forth, and we learned that sine and cosine waves are considered to be sinusoidal. And we learned about what their graphs look like and everything. And so what we're going to do today is look at an application with harmonic motion. Um, Harmonic motion goes on all around you all the time, but it's periodic motion. In other words, the pattern of the motion occurs over and over again at regular intervals. And then when you start to graph like positions of objects that have harmonic motion with respect, their position with respect to time, you start to see these sinusoidal waves. Some examples of this kind of motion can be seen when you look at a vibrating guitar string. And then you start looking at the way the string vibrates, and it's sinusoidal. You start looking at sound waves that come out from a vibrating guitar string, and suddenly you see sinusoidal pattern there. You look at things like a swinging pendulum and look at its position with respect to time, and you've got something swinging pendulum. It goes back and forth at a consistent rate, changing position but staying within the same kind of range there. Object on a spring has this kind of motion. All kinds, you can list all kinds: radio waves, TV waves. This stuff's going on all around you, and you can graph the motion, and you start to see the same kinds of waves that same kinds of patterns that we've been graphing. If you don't believe me, we can go online on the internet. St. Mary's Physics online has a lot of cool videos, but this one you can do a search for sound, vibration, wave characteristics, and it's here on YouTube. And they have this, it's really old-fashioned. It looks like one of those old 1920s or 30s types of TV shows or cartoons or whatever, but it gives you a picture of what's going on. So like if you hit play here,
we can record pressure variations in sound waves with this kind of instrument, an oscillograph. Sound waves are striking the diaphragm at the left. The stylus records the sound waves as a graph. Later we shall use such graphs to represent sound waves. Condensations cause the stylus to move upward. Rarefactions cause it to move downward. So far we've seen how sound waves are produced. Next we'll identify three auditory effects of musical sounds: loudness, pitch, and quality.
so there you go. You can see that sine wave pattern. So the sound waves are hitting this plate or whatever here, and that's making the arm move up and down in a periodic fashion. And it's giving you a picture of what the sound wave would look like if you could see it. It turns out objects on springs end up doing the same kinds of patterns. Like if you imagine that this was a spring here instead of a plate that these sound waves are hitting, you'd end up with the same kind of pattern. So we're going to look at how to model this simple harmonic motion using equations and like dissecting these equations. So we're going to ignore variables like friction and air resistance for now. If you want to get into more depth about incorporating those kinds of variables and so forth, physics classes will do that for you. So this is just a slight introduction to simple harmonic motion. But ignoring that, as we've seen, motion looks like a curve, sinusoidal. Okay, so let's say that we have an object on a spring. We have a spring that's hanging down here. We have an object, weighted object hanging from it. Okay, so this right here is going to be our equilibrium point. you do this, so for this axis, 0, you got equilibrium, then you go 1, 2, 3, 4, etc. -1, -2, -3, -4, etc. So this is the d-axis, the distance axis. How far is this object displaced from equilibrium? And then this direction is time. As this is bouncing up and down over time, you're going to see a wave being traced out like that as it's bouncing up and down. So we want to see how to model that. So the motion looks like a curve or sinusoidal. So we can either use y equals a sine bx to model this with the form equation, or you can use y equals a cosine dx. Okay, so the y-axis, the d-axis, we can replace with d. That a, amplitude, we're going to use a lowercase a here. But that's the max displacement from rest. Then you got either sine or cosine. And then instead of b, we're going to say omega, and instead of x, we're going to say t. So the period is going to be 2 pi over omega, where omega is greater than 0. That's going to be the time it takes to go through one complete cycle. Okay, and that's going to be the breakdown of how we're going to incorporate the equation with this kind of behavior. If you have d equals a cosine omega t, that's for object at greatest distance from rest. In other words, like you pull a spring down, pull the object down and then let it go, or you push it up and then let it go. Use the cosine one. If you think about it, the cosine graph, the typical, y equals cosine x, it starts like at 1 and goes down and then comes back up, down to -1, comes back up. So if your spring is either up here or way down here, at its maximum distance that it can go, then use cosine. If the spring is at rest, use sine. Because sine, if you think about sine x graph, it starts here at 0, goes up, comes down. So if it's here at rest, use the sine function, and that'll work for you there. But that's the breakdown. Rest is where d equals 0. So rest is this line here. This part of the y-axis, or the d-axis in this case. Alright, so let's see how that translates into trying to write an equation. Alright, let me do a word problem basically with you about how you make that happen. If you have an object that's pulled down a distance of 16 centimeters from its equilibrium and then released, and let's say that this object, for it to do one complete oscillation, it takes 6 seconds. Okay, so you have object on a spring, on an object on a coiled spring, is pulled pulled down 16 centimeters down from equilibrium, so from d equals 0. So in this case, the y-axis is the d, the distance, and then the x-axis is t, or time. Equilibrium, and released. Then from there, one complete oscillation takes 6 seconds. So for the time it takes to go from being let go to bounce all the way up and then bounce all the way back down. And remember, it's going to bounce all the way back down because we are ignoring friction and air resistance and that kind of thing. So it's going to be perfect bouncing up and down indefinitely. Unlike real life, you do that with a slinky, it's going to eventually quit bouncing and just hang there because you have friction, air resistance, that kind of thing. So it's pulled 16 centimeters down from equilibrium and released. One complete oscillation takes 6 seconds. Alright, so let's find give the equation first. Give the equation that models the object position at time t. Okay. Now, if we're pulling it all the way down to 16 centimeters, that's going to be its maximum displacement from rest. We're doing it from a distance from rest. We're going to use d equals a cosine omega t. Well, we're pulling it down. We're going down into the negative direction. So a is going to be negative 16. And then omega, remember 2 pi over omega, where omega is greater than 0, is your period. So we need to figure out what omega is. We need to figure out how to do this here. So omega is 2 pi over whatever the period is. If you just do a little algebra there and solve for omega. Multiply both sides by omega and divide both sides by period. Well, we're told the period in the problem. It says one complete oscillation takes 6 seconds. That is the period. It takes 6 seconds for it to go through, to start from down here, go up, come back down. It takes 6 seconds to do that. So put a 6 here and reduce, and that'll give us omega. So we get pi over 3. So put pi over 3 right here. And now we've got an equation to model the behavior of the object on this particular spring. Okay. Now next, let's figure out the position, determine the position when time is 1.5 seconds. You can do this for any amount of time. And you remember, time you're going to be going forward, so it's going to be some positive value. You can start with 0 or go up and go up. So you got d is the position. That's the distance from equilibrium. So we got negative 16 times the cosine of pi over 3 times 1.5. So that's negative 16 times the cosine of, and then you do a little simplifying here, you basically get pi over 2. And what's the cosine of pi over 2? Well, it's 0. So you get d equals 0. So what does distance equals 0 mean? Remember, d is how far, this is the d-axis, so it's how far your object is from that equilibrium point. If d is 0, that means the object is at equilibrium. Now, equilibrium means, if you hadn't pulled on it and it was just sitting there resting, the object would be sitting around right there at 0. Okay? And then finally, what is the frequency here? Okay, frequency, if you want to define it, what is frequency? That is how many cycles are completed in one time unit. Okay, so a period, since a period is 2 pi over w and tells you how much time for one cycle, then frequency is 1 over period, which ends up being omega over 2 pi. So in our case, we had found out that the period we knew was the 6 seconds there. Up here, no, period was 2 pi over omega, omega being pi over 3. But we found it's 6 seconds. One complete oscillation takes 6 seconds. So the question is, when one time unit in 1 second, how many oscillations are there? Well, there's going to be 1 over 6th oscillations in 1 second. Because as 1 second passes, you have 1/6, and as 1 second passes, you have 1/6, and so on. And once 6 seconds pass, that'll be 1 oscillation. So the frequency is 1/6, and then the so frequency, like how often do these occur in a time unit? That's a frequency. How frequently do these occur in a time unit? 1/6 of them occur in a time unit, 1 second. And then the period, well, how long does it take for one whole one to go through? That's the total of 6 seconds. So you can get frequency by just doing 1 over the period, doing the reciprocal of the period. All right. Let's do a little bit backwards. Let's take an equation and let's break it apart. Let's say we're given this. Let's see what we can find out from this equation about the harmonic motion. T is going to be in seconds, the time is going to be in seconds, and d, the distance, is going to be in centimeters. In this problem, A is 12. That tells us the max displacement. So absolute value of 12 is 12. So apparently this object, like if it was on a spring, it's going to go 12 units up, 12 units down from equilibrium. Omega is pi over 4. And since the period is 2 pi over omega, we've got 2 pi over 4 That's going to equal 8. So it takes 8 seconds for one cycle. So like if you take a spring and an object on it and you scrunch it up 12 centimeters above resting and then let go, it's going to take 8 seconds for it to drop all the way down to 12 centimeters below rest equilibrium and then pop back up to 12 centimeters above equilibrium. It takes 8 seconds to do that. But then for each second, the frequency is 1 over the period. Frequency, it's going to be 1 over 8. That's telling us there's 1/8 of a cycle per second. And that's all the information we can squeeze out of there. Okay? Now before you dive into squeezing information out of equations and writing equations, I had a couple other little fun things I wanted to point out to you. I already had a little clip of this video. I encourage you to download it or go to YouTube and watch it. It's nice in that it's a visual. It's not terribly exciting, but it's a visual. But then there's a couple other videos I'd encourage you to check out. One is about Gallup and Gertie, the Tacoma Narrows Bridge collapse. Gallup and Gertie. Tacoma Narrows in Washington, 1940. The bridge basically collapsed. We built it. It was a beautiful bridge. But they found that with high winds, the bridge would jump up and down. It was an example of transverse wave action. Like you watch it, and it was transverse waves rippling through the bridge. It would kind of, they called it galloping because it looked like the bridge was galloping like a horse. It was jumping up and down. And eventually the hot winds got high enough, and it just couldn't stand the stress of that, and it collapsed. There was a little dog on the bridge that went down with it. But the people who were on the bridge, they shut down the bridge that day because it was galloping so hard. But you can watch this footage of it galloping and then falling apart. It's kind of interesting. And since then they built a new bridge, and I don't know if it's new anymore, but they built a bridge after that they made sure to engineer so it wouldn't gallop like that with the winds and stuff. But it's just an example of why we need to understand sinusoidal wave action. Because if you look up transverse waves, you see that sine and cosine waves are basically transverse waves. We need to understand that kind of action and how physical forces can cause it in objects or in matter. So that's something fun to watch. And then another one that's kind of fun to watch is this one about standing waves, like making standing waves with Proud Dude here. I think it's U.S. Naval Academy. They have a 120-foot tow tank, and as you watch it, they're generating waves, like sinusoidal waves, but then something interesting really happens is that as the waves go down, that but as those waves start getting generated on one end, they start traveling down, and then when they bounce off the other end and start going back, they run into the waves that are coming towards the forward still, and it produces something called a standing wave. It's rather kind of fun to watch to me, but another example of sinusoidal action. So Naval Academy needs to be aware of what can happen in water since they are responsible for being out in the ocean. Just be aware of what happens with waves and so forth. But to me, it looks kind of like the waves are dancing or something. I just thought that was interesting, so I just wanted to highlight that. But there's a lot of stuff, if you're into physics and into actual real life, like when are we ever going to use this examples? Just start doing searches on waves and physics and things, and you'll see a ton of stuff. So there you go. Up there you see the equations and so forth. It's rather interesting, isn't it? I'll try to imagine being in a boat in there right now. But I'll let you watch the rest. I don't want to spoil it. But there you go. So thank you for joining us. That's about the extent of what we're going to get into with harmonic motion. If you want more, take a physics class. I guarantee you'll get lots more in a physics class, but that's at least an introduction. Okay, so thank you for joining us, and I'll see you again soon. Rumor has it we're going to probably be looking at trig identities not too far into the future.